Some days you don't want to do the hard stuff. Most of the time, you don't want to do the hard stuff. But here we are. Hi there. How's it going? Welcome to another session of Brain Training, a place where I train my English while I'm trying to explain LeetCode solutions. And for today's session, we're going to continue with the needs code roadmap. And the next question is valid anagram. Let's head over to LeetCode, the website where all those questions came from. This question asks us to tell whether or not two strings or anagrams. And the first question is, what is an anagram? Basically, anagrams are two strings that has the same letters. Simple as that. This problem, you can have two strings that are exactly the same, and they are considered, and they will be considered anagrams as well. How to check whether or not two strings have the same letters? The simple way, or the brute force solution, if you will, would be sorting both strings and then compare the result to see whether or not they are equal. That's the easy way to do it. Easiest. That being said, I will write the solution and then explain after to make this easier to see. I think it's here. Now, give some zoom. This over here is the entire code we need. We are just sorting both strings. In Kotlin, we have to convert to char array. We cannot sort the string right away. We have to convert first to a char array and then sort it. And after that, we just compare the two strings. So just let me show in an example what's going on here. This is what we are doing. We're just converting the string s. We're just converting to this char array and then sorting both arrays and just comparing both arrays to see if they are equal. And this is the simple way to solve this problem. Not a big deal, right? We can also check if whether or not those strings have the same length. If they don't, we just return false. We don't even need go through this conversion and sorting because we already know they are not equal. This is how we do it. Let's run this real quick just to confirm that we pass, and that's it. Not a optimal solution, but get the job done. Get the job done. Yeah, the next step is tell formally what is the performance of this algorithm and how can we improve this. The time complexity of this algorithm is the well-known big O notation for sorting. Is O n log n. This is a well-known time complexity for the sorting. Yeah, this is the operation that takes more time to be performed. So this is the overall time complexity. N log n. And for the space complexity, for the Kotlin version, we need a extra space because of this char conversion here, char array conversion. So we take the string and we use extra space to store this char array. So we can sort the array and then compare. So we have a space complexity of n. where n is the size of the string. That will be the size of this char array. Now it's time to improve this. So the first thing we have to do to improve this is take at consideration this constraint over here, that each string consists only of lowercase English letters. That's the most important information, because with that we know that we have at most 26 unique characters. The second thing you should know is that we have a technique that we can use here. That is, call it, I don't know if this is an official name, but I like to call like this, a frequency counter array. This is another technique. We're going to use this technique to keep track of the frequency of each character within S and within T. So third thing you should know is ask operations. You have to have an idea of ask code, a little idea. Let's improve this. With all this information, we know that we have to create this frequency counter, but we're going to create we're going to create two frequency counter arrays, one for each string. After that, we have to count the frequency of each character that within those two strings. How are we going to do this? I have to draw this so we can understand what the heck is going on with this code. Let's use the first example that I got. Let's see. S is this string, and T will be this string. We have those two strings, and now how does our frequency counter looks like in code? Looks like this. Let me zoom in this real quick. Yeah, our frequency array, or frequency counter array, looks like this. 25 positions, 25 indices, 25 indices, 26 from 0. Yeah, 25 indices starting from 0. So we have in total 26 positions that we can fill in with information. They all start with 0, because int arrays in Kotlin they are all filled in with zeros. So this is how they look like. Secondly, now that is the tricky part. We have to know, right? We have to keep in mind that a character is represent as a ask number, like this. Let's say that a character is represent in our language as a number, a unique number. This is where the ask code is important. We know this is represent as 997. I know this because I search at Google. I Google it to know this information. But anyway, and B is represent by 98, and so on and so forth up into Z. That is the number that the ask code is 122, if I'm not mistaken. Now with all this information, beautiful information right here, we can find the positions where each letter goes, because the intent here is to start 0 position should have A, so in alphabetic order, A, B, C, so on and so forth up into Z. And we're going to do this. Look how clever is this solution. You're never going to come up with this in your entire life. Subtract A from, we can subtract A from the character we are looking at. So A, we can represent at 9, 7. This will do, this will result at 0. The next, if we want to find where, which position B will go, we just subtract A again from this, 9, 7, and the result will be 1. And up until Z, that the result will be, you guessed it, 25. All positions, each position will be, each letter will be in the right position because of this operation over here. Just subtracting the ask code of each character we have. And we can find the position where the letter should go. With this information, we can count how many A's, how many B's, how many C's, and so on and so forth each letter has. And then we can compare both arrays to check whether or not they contain the same counter in the same position. That would mean that these two letters have the same unique characters, the same amount of unique characters. And therefore, they are considered anagrams. That's beautiful. This is such a clever way to optimize a code. So the code goes like this. After all this explanation, the code looks like this. That's the part that I was explaining. So we are looking at a specific string in this loop. So the current not string, we are looking at the specific character, subtracting the hash value, the ask value of A from this character to find which position this specific character is located in, or frequency counting array. And then we're going to increase the current frequency of this character. After counting each character, we just need to compare both arrays like this. And this is how we compare both arrays in Kotlin. We cannot use the equal sign for int arrays. We have to use this content equals. The equal sign doesn't work for those type of arrays. But anyway, and of course we now, because we are using for loop operations, now it's really important to check whether or not the strings has the same size or length, if you will, before we go ahead and iterate over the strings and count their frequency. Let's clean up this now. With this all cleaned up, we can run the code and see whether or not we messed this up or we did the right thing. We got this right. Ooh, beautiful performance. Look at the improvement we got here. It's beautiful. That's how we improve it. This is how we do it. The time complexity for this algorithm now is the beautiful linear time, O of n. Linear time because we just iterate over the entire string, both strings at the same time, and we are using the same extra space. Oh, space complexity. Oh, rather, actually, and for space complexity, we have this complexity. We are using two, we are creating two arrays of 26 to keep track of the frequency of each character. But as we know, big O notation don't take as consideration constants, so the space complexity will become constant time because there are now doesn't matter how big is the strings, we're always going to use the same size of arrays. We can improve upon this using a single counter over here, and we can because we can use just a single frequency array to not having to use two arrays. But I'm not going over this. Maybe I will. This is just a cleanup. We can clean up this even further by using a single array like this. We can use a single guy, call this frequency count array. And rather than, and when we are iterating over each string, we can just increase one and decrease another. With this operation over here, if they have the same frequency of unique characters, we know that all elements should be equal to 0. Because one is increasing, but another one is decreasing. So in the end, they should all be 0 if they are equal. So let's give this a try and see what we got. Same improvement, same result, but a little bit cleaner. But in my opinion, this is not that easy to understand because you're doing two things in the same array. But in the end of the day, we have the same result. The first approach, the first solution I thought I find easier to understand. See you in the next one. Bye.